So this is the outline of the talk. First I'll explain the object that we are studying and why finite version of that object is hard, why the infinite version is hard, the tractable classes that we have, and we'll conclude. So this is just to highlight the use for the model. So suppose a teacher gives these two homework problems, and next day student is asked one of these questions, and student for some reason hears only one of them, the last part of them, and so how should the student answer knowing that the teacher is asking one of the homework problems? So the point of this question is not to really answer this question, but what we want to highlight is how do we model these scenarios, and so this is a simple enough model to say that. So the teacher asks questions and the student is not sure. This shows he is not sure, and the payoffs will depend on the questions themselves. So this is the setting. So an extensive form game is a generalization of models of these sort, and so this is how it's defined. A finite extensive form game among n players is given by a tree. So the tree has edge labelings which give the actions of the players, and the turn function gives which is the player who owns the node, and the information partition, that is the new addition in the imperfect information scenario, which basically says the nodes which the player is uncertain about, like exact location of where he is uncertain about. So this is what we are trying to say, and we put this restriction that we allow information partitions on only nodes where it's player's turn to move. So yeah, and a preference relation over maximal paths and place. So yeah, so standard definitions. So this is what in the previous talks, if you heard, like uniform strategies is exactly this. Like you want a strategy for the information set and not the individual nodes. So strategy is mapping from so once again. So here you can notice that we have an information partition for each player, and what I mean by an information set in an information partition is equivalence classes of this form. And yeah, so a strategy maps every information set to an action, and a strategy profile tuple of actions, and play is consistent with a strategy if whenever it with a strategy for player I, whenever it is the player I's turn to move, the action made is consistent with the strategy. So this is the basically. So how do we bring about preferences in this? How do we use them? So a strategy is a dominant strategy if it is better if for every play of the opponent and every strategy that the player itself has, the dominant strategy is definitely at least as good as any strategy that the player has. That's the notion. At least as good. So that's what we want to say. So in this setting, we are only interested in preferences which are like binary, that is win-loss preferences, and we call the dominant strategy the winning strategy. So specifically, the problem we are interested in is that of a coalition of players. So we say a coalition of players. So we just lift this to a coalition of players. The dominant strategy. If there's a strategy for every player in the coalition which is better than every other of its strategies for any play of or for any strategy of the opponents. So this is what it means. And additionally, we have this condition that all players in the coalition have the same preference over the plays. So makes sense. So these are the questions of interest, and we'll be only interested in the second one. Yeah. So additionally, there's a assumption that we'll be using that we'll be studying a very restricted class of games, namely the games of perfect recall. So what we mean by perfect recall is for for any two vertices in an information set, if we try to map the histories, if we try to map the information sets that we see on the path from the node to the history, this string matches for both for all nodes in the equivalence class. So this is what we mean by perfect recall. So I'll just show what I mean by this. So this is like a game of imperfect recall. Like so the player here has forgotten that he made a move. This is not really correct. You need this also. It's an equivalence class. So actually this doesn't highlight everything, like the real nature of what we mean by imperfect recall. So it also means that like if we are in two subtrees and a player is certain in which subtree it is, then we are not allowed to be uncertain at a later point of time among the nodes here. So this example doesn't show it, but the definition is clear. So a perfect information game is one where the information sets, there is only one node in every information set, and perfect information games are easy in a particular sense, like because we can look at the subgame, pick a winning strategy here and compose it and come upwards. Yeah, so right now we're only interested in the finite version. So I'm trying to tell you why the finite version of imperfect information games is hard. So yeah, so imperfect information games are hard because of this lack of composition, of not being able to compose strategies of sub games. And this example is actually the NP hardness proof of. So given a 3CNF, it's a reduction from a 3CNF to a game. So what I mean by C1, C2, C3 are the clauses. So I'll tell you the game. So there are three players, 1, 2 and nature, and nature picks a clause, and the player 1 is told the clause, but player 2 is not told it, and player 2 is told a literal, but not told which clause it is, and a play is winning if it can reach, if the clause is satisfied, if this assignment makes it true. So we have a and over or kind of setting. So yeah.
I mean, normally in imperfect information games, positions that are not distinguishable for player 1,
Yes.
I mean, the moves should be, the available moves should be the same.
Yes.
Is
So so in this scenario,
what I mean is that the literals in the different clauses.
okay. So but that is not.
This is fixable.
Yes, but I mean it's allowed. I mean I don't see why it's not allowed. Like you can have different moves, but.
But the idea is that if the available moves are different, then you may be able to distinguish.
Sure. You may be able to distinguish, but.
So it's just a question of encoding this outcome. Okay.
Yeah. Sure. Yeah. So this picture is sort of incomplete. So we have these things here also. I just drawn that. Yeah, the picture is. But yeah, but I think she meant that player 1 for player 1. Okay. So these lines. Sorry. Yeah, it's player 2's information set. Yeah. So here we have a addition to the.
Yeah, that's the difference.
Yeah.
In the original thing,
You allowed on.
only on.
Yeah.
Okay.
Yeah. So what he's saying is that earlier I had mentioned that we allow information partitions to be formed only on the nodes where ownership is available. So like you can see, like here we allow information partitions on also the nodes where player 2 has no ownership. But this is to make a point that player 2 doesn't know which clause was chosen. So in this setting, you can see that if the literals are the same, then the player 2 has to choose the same valuation, and you can see why this is hard, because like you can't just look at some clauses and decide. You can't compose it upwards. So this is to make a point that it's hard, and so So in infinite games, we study via particular finite representation of infinite games, which is via this game graph or arena. So, so it is a label transition system, and additionally with the fact that every node has a has an observable. So it's like a signal for each player. So whenever you reach a node, there's a signal for each player, and a player can observe only its own signal, known as a signal. So this is how we model it. For every vertex, we assign observables, and whenever that vertex is reached, this observable is transmitted, sort of. Yeah. So additionally, we assume that the structure of the game graph is known to all players, and that the turn functions are layered. That means you don't have a situation where it's player one's move here and you this sort of situation. Like on one action you move to a node where player 2 gets to play, and on I'm saying yeah, it's a turn-based game. That's all it means. It's a turn-based game. So this is an example of it. So this is the reason why I have used this example. I will use it later on. So this is this is what the game graph looks like, and from the game graph we unravel it to get the game tree. So the nodes of the game tree are finite plays on the game graph, and yeah, and how every player observes each play. This is how we identify it. So given so for the previous game, this is what its unraveling would look like. So please ignore everything else. Just look at. I just made this to make a point of how the equivalence classes would look like. So this is the observable of player 1. This is the observable of player 2, and so on these plays, you see there's a one equivalence relation only when the left side matches, and two equivalence relation only when the right side matches. So it's just to highlight that this is how the information partition looks like. So additionally, we said that every player owns a node, and only one player is allowed to own a node and stuff like that. So this is slightly different. Here the setting is that of every node. So here the setting is that of two players playing against nature. Two players playing against nature, and what we are saying is that every node, each player is allowed to make an action, and if this results in many nodes, the nature chooses which one to choose. So it's like the two players choose an action, then nature chooses, then two players choose, and then again nature. So both these settings are equivalent. So for the example, this is easier to see. Yeah. Yeah. So winning conditions on infinite games. So in the finite case, we gave preferences on finite plays. So here we are only interested in win-loss preferences. So we say the winning plays are a certain subset of the possible plays in the game graph, and we use this parity condition. That means on the game graph, you are additionally given numbers to each node via this, and the set of all numbers which occur infinitely often, if the minimum of those is odd, you say the play is winning for the coalition, like 1 and 2. Yeah. So additionally, we have this condition of that the winning condition respects observational equivalence. So this is very strict condition. So what it says is that if two plays look alike for any of the players, then and one of them is winning, then the other one also has to be winning. So it's just closing it under this. Yeah. So yeah. So in the infinite case, why are perfect information games easy? One is obviously you can look at the sub games pick out the winning strategy and compose it. And additionally, this is the reason, like, you just need to look at up to certain finite level. So typically the argument in perfect information scenarios, it goes like, if a player could have deviated and done better or worse, then it could have done it earlier. So you just need to look up to a certain finite level. And for parity conditions, this is enough. This sort of argument is enough. Yeah. So, but imperfect information games are known to be hard. It's undecidable. So there are 3 papers which show this, and all 3 of them in 3 different settings. So first one is a setting of this multi-person Turing machine. Second one is some asynchronous system. So I'm not familiar with the details. So to me, the last one is the most clear of all 3 to show what is actually going on. And so this work is sort of, you can say that, like, it starts from there. So you can see that in infinite games, you can have your information sets can be, like, it can keep on growing. And in the finite case, we saw that the hardness of finding uniform strategies comes from the fact that you have to choose the same action for nodes which are in the same information set. So this is what makes it hard. So in infinite case, you are allowed ever growing information sets. So one would think that is what makes it hard, but that's not really the case. So since the number of states of the game graph are finite, and states are all that determine the future possible plays, you can, if 2 nodes, if 2 plays end in the same states, then the restriction of uniform strategies are not, it doesn't add anything, because you can follow the same play here and you're guaranteed to get the same results. But that means they are easy, but so then there is something else that makes it hard. So this is what makes it hard. So I say knowledge and stuff, so I don't know what it really means. So it's a very rough idea of what knowledge, and what I mean is certainty and uncertainty relation. That's what I mean by knowledge. So why the infinite games are hard is, so in this situation you can see that, so in this move, the player 1 chooses an action, this action, player 2 chooses this action, and you have 3 possible next states. But and you can see that player 1 can distinguish between these and this, and player 2 can distinguish between these and this, like, only as partition. So this is what makes it harder. It's not the fact that the information sets themselves are growing. It's how the sort of the lack of common information between the players that makes it hard. So it is these ever growing chains that makes it. So how we can read this is, so every player knows which information set he or she is in, and so when the play reaches here, the player 1 knows that he's in one of these 2 states, but player 2 will know that the play is in one of these 2 states, and but then the player 2 can think that player 1 is either here or here, and so this keeps on growing, and this is what makes it hard. So this is the essence of the hardness, and so this is actually the undecidability proof also in some sense. So the strategy for this game, the joint strategy for player 1 and 2 in this game is that of Philippus. So what I mean by this is that whatever stage the players are in, you will have to play that many crosses. So this is the strategy. I'm not going to the analysis, but so that basically means we don't have a memoryless, or we don't have a strategy that is limited, which is finite state. So yeah. So yeah, I'll just there's no bounded memory strategy. Yeah. So I'll just say one more thing. Yeah. So this is the game, this is the crucial part, this part of the graph. So this part of the graph you can code it up you can code up Turing machines in this part of the graph, like one move at a time, and this will give us the undecidability proof. I just want to say that. Yeah. So our objective was to look at are there any tractable classes to for this problem. So like I said before, it's this ever-growing chains that cause the problem. So one thing is you want to limit the size of the chains. So are there natural conditions to do it? So this is what we came up with. One is that there is a notion of recurrent certainty for players. That means along any play, a player is guaranteed to be certain at certain number of certain infinitely often. So in this example, if you see, like, if I'm guaranteed to be able to merge these two positions at some point of time and infinitely often, we can sort of limit the size of these chains. And so that is one condition. The second condition is that of hierarchic knowledge. So what I mean by local property and locally global property is that, so one condition is on that of information sets of individual players. That means I'm saying that if a player looks at its own play, there are certain points infinitely often where it knows exactly where it is. And by locally global, I mean it's not that we are posing restrictions on the information sets of individual players, but on that of how these chains look like. So that is the thing. I'll explain what I mean by hierarchic knowledge. So these are known to be the class of games which have hierarchic knowledge are known to be decidable since Peterson Rife. So we'll show something else about that. So given these two conditions, we have two questions. One is that of whether given a game graph, can we determine whether the game corresponding to that game graph satisfies these properties, and other is if it does satisfy, can we get a coordinated winning strategy. So now I'll come back to the definitions of the two properties that we mentioned. So the first one, we say an information set for a player I is certain for a player I if for any two plays in that information set the last state is the same. So we are not saying that they end in the same state. We are saying that so we are not saying that eventually you are guaranteed to like sort of merge into a node. What we are saying is you are guaranteed to be at the same state. You might not know which how you arrived at that state, but you are guaranteed to be at that state. So recurrent certainty is what we define as achieving this condition like infinitely often. So initially we were looking at some way of putting some structure to the game graph so that these things are achieved, but what we did was something different. So I'll come to that, what we did differently. So like I said, we are looking at so what makes imperfect games hard is these long chains, and for the purpose of proofs and also for the reasoning involved, like we want to say that we are limiting these chains, and what we call those chains are these epistemic models. Basically, instead of calling them just a set of plays who are connected, we just give them a name, and so this is how they're defined. So basically on a level so all chains of this sort, that is what we aim to capture by this definition. So we call a level of we call a level of in a level, if the set of all plays where some player is uncertain, we group them together and call it an epistemic model. And yeah, so this is what we have, like that. Yeah. So given a game graph, we can actually efficiently test this property. That means whether recurrent certainty is guaranteed along every play. This is something that can be tested. And so how the proof of this goes is sort of straightforward. I'll tell you why it works. How it works is much straightforward. So basically we want to look at all information sets that are produced in every possible play, and we want to sort of partition them into ones where we are certain and ones in which we are not certain. So why do we have a good efficient procedure for doing this? Because every information set I can uniquely identify by looking at the I projection of the play. So that is one reason. And now given this, to test that information set satisfies this property of certainty, I need only finitely many witnesses. So what I mean by that is, I just need to find two paths for which this property doesn't hold true. So this sort of makes it easier to do that. So yeah. So how we actually do it is by we take two copies of the game graph, do a product construction, and if you look at that product construction, this is easy to determine. So as a corollary of the proof, not the theorem actually, we get this, that in a game graph, if you insist on having recurrent certainty, it has to be periodic. Like, so in the sense, you can't say that. So like I said, you can code up Turing machines in this setting. So you can't say that at the end of the computation go into a perfect scenario or something. Stuff like that you can't do. So this is what this basically means. And yeah. So then determining the winning condition. So it's not. So this is not that straightforward in the sense that. So what I'm not saying is that, you know, you play and then there's a level where everyone knows what they are doing, and then again you play and then everyone knows. That's not what's going on. What I'm saying is, individually each player knows this infinitely often, but doesn't mean the other players know that too. So it is possible that in one stage I know where exactly I am, but other player is still confused, and later on the other player knows, but at that time I don't know. So this sort of scenario. So yeah. So yeah. So yeah. So how? So we can. So we have a decidable procedure to test the existence of a winning strategy in games of this sort. So this comes from the previous result that in game graph, guaranteeing recurrent certainty amounts to guaranteeing periodic certainty. So given that there's a maximal period for every player, maximal period in which every player is guaranteed to be certain, we can limit the size of the chains, sort of. So yeah. So this is what knowledge hierarchies are bounded, and so then you can look at every knowledge hierarchy, or like we call it the epistemic model, and those will be the new states. So we translate it into a perfect information game, and so those will be new states which of the perfect information. So we get this by a sort of exponential blow up. So exact bounds I don't know, like I'm just still working out. So by hierarchic knowledge, hierarchic knowledge. So, like I said, games in which the knowledge of the agents is hierarchic are easy. What I mean by hierarchic is only situations of these kind occur, like so I say player 1 is uncertain among these two, and player 2 is not allowed to be uncertain like this. You can allow this, and then another player can only. So it's always there's a subset ordering on relation. So only these kind of uncertainties are allowed in the game. So this class of games is known to be decidable. I mean, yeah.
So you think this hierarchy is, well, after picking a number of moves or including?
No. What I mean is, so at every stage of the game, so like I drew these chains, right? Like one and so this is not hierarchic because player 2 knows something. Player. So
No, yes, this
yeah.
I understand. So the information sets have to be included.
Yeah, inclusive. Yeah.
But even, well, even taking into account information sets with well, temporal loss, so across different levels, or just on one?
Just on one level.
Just
on one level.
Okay, because I could mention this inclusion even taking into account memory loss.
Yeah, so that's the thing. You lose stuff like that. Perfect record. Yeah.
Sorry, I missed the obvious part.
Yeah. So this is what is formally written as this. Like we allow only information. Knowledge hierarchies of that form in which things keep on growing, and yeah. So and then we say that a play is recurrently hierarchic if these sort of information sets occur infinitely often. So what you should notice is that we are not limiting the size of the knowledge hierarchy as such. I'm just saying that they should be inclusive. So you don't care about. We are not actually limiting the size, but just a structural condition. So this is what I meant by locally global sort of.
Yes, last condition is some beta IM.
Oh yes.
Beta IM and beta IM.
And yeah, pi 1, pi 2. Yeah. Sorry. So again, to test whether. I'll call these chains as epistemic model. I mean, they are exactly that. So we can test whether an epistemic model is not hierarchic with only two plays. We just need two plays as witnesses. So this is exactly the previous proof we can sort of lift into this setting, and we get a decidability there. And again, like why it works is. So earlier we could represent every information set via the observations that you made. So for every observable string, that means if I see, like in the example, if I see 3 shaded dots, I know the possible place that player 1 is in. So to do the same thing here, we need to identify individual epistemic models and not the information sets. So how we do that is we add a new player who is as uncertain as any player. So what we mean is, like, if 2 states are uncertain for any player, then it is definitely uncertain for this new player. So what this does is, like, in these sort of scenarios, this chain sort of scenarios, we have this new player called N who is definitely as uncertain as any of them. So we can get the set of plays which correspond to an epistemic model. Is that clear? Like, I can ask. Yeah, sure. Yeah. So again, how we do this is, like, we take 2 copies of the game graph. We take a product, and in that, because again we need only 2 plays to determine whether a epistemic model is unhierarchic. So so that can be done. We just need 2 copies of the game graph, and you look in that and you will find out what you need. So because these are essentially finite systems, you get this. Yeah. Yeah. So so here to the existence of winning strategy is decidable, but the previous techniques won't work, in the sense that there we limited the size of every information set, and that's how we did this this part of the proof. Here, like I said, it's not necessary, we are not necessarily limiting the size of the epistemic model, we're just saying that there are certain structural conditions. So that is because given, so there are only so given 2 epistemic models, we can there's a notion of a homomorphism between 2 models, which allows us to sort of quotient the whole set of epistemic models to only finitely many. So what this means is like so if there are like 2 states Q1 and Q2, so 2 plays end in Q1 and Q2, and now suppose there are 3 plays, that one is Q1, Q2 and again Q1. We are allowed to shrink this. We are allowed to keep only 1 copy of each state. So we couldn't do this previously because, like you saw, so if it is Q1, Q2 and Q1, so this is an information set, but we can't shrink these 2 copies because these copies are constrained by additional conditions which are given by the chains. So we can't do this, but in case of hierarchic epistemic models, we can do this. So there's a very clean notion of what a homomorphism between 2 epistemic models looks like, and so by that we can say that if you look, I mean, every epistemic model, you need not consider every epistemic model. There are only finitely many ones which you need consider to know what the winning strategy is. So you can just quotient it. Yeah. So and this this comes with a non-elementary blow-up because the number of possible epistemic models in with finitely many states, there are non-elementarily many. So basically the game graph, so the reduced game graph into the perfect information case, it looks like every node is one of those minimal epistemic models, and you are playing among in that setting. Yeah, so I'll conclude. I think I'm done. Yeah. So we saw why imperfect information games are hard, both for the finite case and infinite case, and breaking up these chains, that's what we need to do, and we have 2 tractable classes in this setting, but we have some problems in the current setting. One is that this condition of observable winning conditions is very, very restricted, and I want to look at cases which are more natural. I want to look at definitions of winning conditions which are more natural in the imperfect information setting.
I thought you can always reduce the problem to such things, no?
That is for 2-player case. So this. So yeah. So and additionally, this condition of perfect recall in a distributed setting. By perfect recall, I mean also, so this, even the synchronous part comes in by our definition of perfect recall. So in a distributed setting, to guarantee synchronicity is not very realistic assumption. So and another problem is like every known tractable classes of these games, the proof is via reduction to a perfect information game with a blow up. It's power set construction over and over again. So you haven't really found anything new in some settings, in some sense. Yeah. So what I hope to do is, so this is a result by Jam and Sunil, that determining Nash equilibria in infinite games of this sort is easy in the so again I should mention. So the public announcement cases are in these settings are generally easier for this problem, this particular problem. Why? Because in our settings, so public announcement basically amounts to having hierarchic epistemic models. So it's sort of subsumed by that. So that is a possible explanation of why public announcement is easy to determine a joint strategy. Sorry.
I don't quite understand this.
Yeah.
Maybe I should. You mean that you can.
So what?
In some way.
So here, first of all, we are looking at joint strategy. That means for a team of players, everyone knows each other's strategies. So they can't really communicate, but beforehand they have decided what to play, and those strategies are known. So that sort of limits how the knowledge hierarchies look like, and they look like hierarchic information sets. So. Yeah, so we know that this is decidable, and so now, but the approach taken is you don't really look at what the epistemic structure is. You just it's algorithmically a good proof, but what goes on internally is not clear. So that is one thing I would like to look at, like is there a natural notion of comparing two epistemic models so that we can, you have an alternate explanation for this. That's the hope. And yeah. So the winning strategies. So this sort of setting of power set construction. So by power set I mean like you expand it. You expand your state space and then analyze it as perfect information games. So it preserves winning strategies, that is known, but I don't know whether it preserves other things. So Nash equilibria is also a strategic property in that sense. So it does preserve Nash equilibria. So given a game of, what I mean by that is given a game of recurrent certainty, if I look at the expanded game, so the reduction that we did to perfect information game, so if we do that and I try to find out what is the Nash equilibria in that game, that matches with my Nash equilibria in my original game, but I don't know whether whether it's true of all strategic problems. So some things are definitely not preserved. So suppose you had like two winning strategies in the original game. Here you will have only one. So some things you definitely lose. So how much do you lose? This is one thing I want to work on. And yeah, obviously more natural winning conditions. So yeah, that's it. Thank you. Something, yeah.
You said that it's only in the case of two players that you can always reduce to observable winning conditions. But why is it so?
So again, this is just hearsay. I don't really know the argument that works there. So.
You have one winning condition for your coalition.
Yes, one winning condition.
One winning condition for a player.
One winning condition for the coalition.